Now let's introduce the support of a sheaf of sets through this exercise. Suppose Z is a closed subset of the topological space Y, and I is the inclusion of this closed subset into this topological space Y. Let script F be a sheaf of sets on Z. Now let's find the push-forward sheaf of F at Q, or Q in Y. By the definition of the push-forward sheaf, we know I star F of an open subset V in Y is equal to the script F of I inverse of V. This is equal to V intersection Z. Now what is the stalk of this push-forward sheaf at Q? The stalk at Q is a colimit over all open neighborhoods of Q, which is from here the limit of f of V intersection Z, where V ranges over all the open neighborhoods of Q. If Q lives in Z, by definition of the stalk of F, this is precisely the stalk of F at Q. If Q is not in Z, then this limit will become f of empty. This is because Z is a closed subset of Y, and V is an open subset of Y. In particular, if we take V to be the complement of Z, and this will become f of empty. But f of empty is a final object. You can easily verify from this cone for this colimit that f of empty is a colimit by universal mapping property. And this completes the proof of part A. Okay, now let's look at the part B. In part B, we define the support of a sheaf of sets to be the set of all the points in the topological space X such that the stalk is point where stalk is non-trivial. And more generally, if the sheaf has value in some category, this condition will be replaced by that the stalk is not the final object. If the category is a category of sets, then the final object will be the one-point set. So this is a special case of this. And in the category of abelian groups, if sheaf takes value in the category of abelian groups, then this condition will become that the stalk at P is non-trivial. Recall that previously we have defined the supports of sections. How to combine those two definitions? The definition of the supports of sections and the definition of the support of a sheaf are associated in the following way. If G is a sheaf of abelian groups, then its supports consisting of all the points where the stalk is non-trivial. But we can interpret this in the language of the stock of G at a point is not zero if and only if this point is in some open subset where there's a section in this open subset such that the germ of this section is non-zero at this point. And this is equal to the union of all supports where U ranges over all open subsets and S is a section of f of U. Of G of U. Should be replaced by G. Now let's prove that natural map from G to the push forward of the pushback of G under the inclusion map I is an isomorphism. Before we start our proof of part B, we first need to unravel what this natural map from G to the push forward of the pullback of G really is. This natural map actually given by the adjunction of the inverse image and the push forward. Remember, there's a natural bijection between the morphisms from pi inverse G to F and the morphisms from G to pi star F. And to show that there's a natural bijection between them, we introduced a set of compatible collections. So the natural bijection from here to here is a composition of those two maps. The first map was denoted alpha and the second map was denoted delta. So this bijection is delta composed with alpha. By our definition, this alpha sends a sheaf map phi from pi inverse G to F to a collection of compatible maps phi sub VUs, where each phi sub VU is defined by the composition of three maps. So phi sub VU is a composition of those three maps. The first one is a map naturally associated to the colimits, because its pi pre-inverse G of U is a colimit. The second one is a sheafification functor. And the third one is our phi. Phi with respect to open subset U. And phi sub VU is a composition of those three maps. And now let's look at the special case when F is equal to pi inverse G. Let us script F to be pi inverse G. And we take our phi to be the identity map on pi inverse G. And we apply delta composed with alpha to this identity. And how about this delta? We define this delta to be the map sending the compatible collection of maps to this guy by replacing U with pi inverse of V. So there will be only one index. this is a sheaf map from G to pi star of f. And now let's get the formula for delta composed with alpha. Now, the action of delta to this guy will replace all the u's by pi inverse of v. And this is what we will get at the end. And now, let's look at the special case. We let the script f to be pi inverse of g and phi to be the identity on this inverse image of g. We apply delta composed with alpha to this identity. In this case, we see that part will become identity. So there will be only two parts left. And this map will be a map from G to pi star of inverse of G. And this is how we get this natural map stated in this problem. Now let's go back to this problem. We let pi equal to the inclusion map I in this case. I is the inclusion from Z into Y. And Z is closed. Then the pi inverse of V in this formula will be replaced by Z intersection V. And this phi praise of V Z intersection V will become. Now let's compute the stock of this map, the induced stock map of this morphism at the point Q. If Q is in Z, we see after taking the colimit over all the neighborhoods of Q, we get an identity map. We see the induced stock map of this part will become the identity map on G sub Q. And since the sheafification in this case will induce an isomorphism between stocks, the induced stock map at Q will be an isomorphism from G sub Q to G sub Q. On the other hand, if Q is not in Z, then we see this part. We know that this part, when taking the colimit over all open neighborhoods of Q, will become G of empty, which is a one-point set. This is because since Z is closed, if we take V to be the complement of Z, which is still an open neighborhood of Q, and you will see this intersection becomes the empty set. And let W take this empty set, and we get our colimit. But this is not a very rigorous proof. To rigorously prove this, you need to draw a cone for the colimit and use a universal mapping property to prove this. In this case, this guy is already G of empty. So you have a test object CW with the associated maps, then there must be a unique map from G of empty to this W. this dotted arrow will be precisely this arrow. It will be the only choice. And therefore, G of empty will be the limit of this limit. So if Q is not in Z, then the induced stock map of this map will become trivial. And so will the induced stock map of this guy. To summarize, the induced stock map of this guy will either become an automorphism on GQ or a trivial map, depending on whether Q is in Z or not. However, in this exercise, it's an extra condition. Since the support of G is contained in Z, if Q is not in Z, Q is not in the support of G, so we can combine these two cases. So when Q is not in Z, both sides of this arrow will become trivial. And this is still an isomorphism between two trivial things. So this guy will be an isomorphism anyway. So we can combine these two cases. So for any Q in Y, this induced stock map is an isomorphism. And therefore, this sheaf map is a sheaf isomorphism. And we are done.